Hello. So in today's lecture, we're going to be going through some revision on the quantum mechanics chapter. So we'll be looking at the problem of taking a Hamiltonian, diagonalizing it, finding the unitary time evolution operator, and then finding a time-evolved state. Okay, so we begin with the Hamiltonian H bar 102, 010, 201. Okay, so you can quickly check that this is a Hermitian operator. Okay, so to diagonalize this Hamiltonian, the first thing we need to do is find the eigenvalues, which means we need to find the determinant of the following matrix. 1 minus lambda, 0, 2, 0, 1 minus lambda, 0, 2, 0, 1 minus lambda. Take the determinant and we set it equal to 0. Remember, this will give us our characteristic polynomial whose roots are going to be our eigenvalues. So taking the determinant, we get 1 minus lambda times 1 minus lambda squared minus 0 plus 2 times 0 minus twice 1 minus lambda. Okay, and again, this must be 0. So just simplifying this a bit, we get 1 minus lambda cubed minus 4 1 minus lambda is equal to 0. We can factor this quite easily as 1 minus lambda, we can take that out, multiplied into 1 minus lambda squared minus 4. And then notice in the square brackets, we've got a difference of 2 squares. We can factor that as 1 minus lambda, 1 minus lambda plus 2, and 1 minus lambda minus 2. That's equal to 0. Simplifying those last two brackets, we get 1 minus lambda, 3 minus lambda, and lambda plus 1. Okay, after taking out the minus sign from that last bracket. Okay, so we've got a product of 3 terms here equaling 0, so we can easily solve for our lambda values. So lambda 1 is minus 1, lambda 2 is 1, and lambda 3 is 3. Now, I like to order the eigenvalues in increasing order. However, that's not compulsory. Yeah, but I like to just be consistent with that. Okay, so those are our lambdas. But if you note, when we took the determinant here, we left out our h bar. So we need to put that back. So our energy values are going to be E1 is minus h bar, E2 will be plus h bar, and E3 will be 3 h bar. Okay, so now that we've got our eigenvalues, we can then find the eigenvectors or the eigenstates. So let's begin with lambda 1 is minus 1. So substituting this into our above expression here, we end up with 2, 0, 2, 0, 2, 0, 2, 0, 2 times x, y, z, because we've got a 3-dimensional eigenvector, and this must be equal to 0, 0, 0. Okay, if you don't know where this comes from, please go back to the lectures on eigenvalues and eigenvectors. Now we can do row operations to simplify this. So we end up with 1, 0, 1, 0, 1, 0, 0, 0, 0 times x, y, z. And this is still equal to 0, 0, 0. Okay, now multiplying this out, we get two equations. X plus z is equal to 0. So x equals minus z. And y equals 0. Yeah. Now, either x or z is a free variable. However, it's not entirely free because we would like our eigenstates to be normalized. So in that case, we can pick x to be 1, which means z is going to be -1, and then we need to normalize that with a factor of 1 over root 2. So for our first eigenstate, we can call it psi1 is equal to 1 over root 2, 1 for x, 0 for y, -1 for z, and the 1 over root 2 such that this vector is normalized. Okay, so the length of the vector has to be 1. We can do a similar thing for lambda 2, so that's equal to 1. Okay, again, substituting lambda, we end up with 0, 0, 2, 0, 0, 0, 2, 0, 0 times xyz equals 0, 0, 0, the same as before. Again, we can do row operations to simplify this. So we have 1, 0, 0, 0, 0, 1, 0, 0, 0. Yes, I've just done dividing the rows by 2, shifting some rows around so that the 0 rows at the bottom. Of course, that's not compulsory, but that's what you should have done last year when you did systems of equations. Okay, so times xyz is equal to 0, 0, 0. That remains unchanged. Okay, so multiplying this out, we get 2 equations. So x is equal to 0, z is equal to 0, but y is free. But again, not entirely free, because we want the states to be normalized. It would be best to choose y to be equal to 1. Okay, that will give us a normalized state vector. So we can write psi2 as x being 0, y being 1, z being 0. And we don't need any factors in front because it's already normalized. Okay, we can do the same thing with lambda 3, which is equal to 3. Substituting this into that expression above, we end up with -2, 0, 2, 0, -2, 0, and 2, 0, -2 times x, y, z is equal to 0, 0, 0. Again, we can do row operations to simplify this. So we end up with 1, 0, 1, 0, 1, 0, and 0, 0, 0, similar to what we had before, times x, y, z, and this is still equal to 0, 0, 0. Okay, sorry, that's 1, 0, -1, because we've got a -2 and 2. They have opposite signs in that first row. Okay, so multiplying this out, we have x minus z is equal to 0. In other words, x is equal to z, and y is equal to 0. So similar to what we had in the first case, either x or z is going to be a free variable, but again, not entirely free because we want a normalized state vector. So if we choose x to be 1, then z would automatically be 1. And we need to multiply our state vector by 1 over root 2, just so that it's normalized. So we have our state vector psi3 is equal to 1 over root 2 for normalizing. X is 1, y is 0, z is 1. Okay, so we have our 3 eigenvalues and our 3 eigenstates. And just a note, remember, since this is a Hermitian operator, the Hamiltonian, we know that the eigenstates should be normalized, first of all, because they're quantum states. And secondly, they should be orthogonal. So I'll leave that as an exercise for you. Check that they are orthogonal. In other words, orthonormal, since they are already normalized. So exercise. Check that psi r inner product with psi j is equal to delta r j. So we already know that they're normalized. Now please just check that they are orthogonal. and then together, this means that they are orthonormal. Okay, but the second part, the normal part, that has already been taken care of. Okay, so once we've got our eigenvalues and eigenvectors, we can now diagonalize the Hamiltonian. Okay, so we can write it as a diagonal matrix. Remember, H can be written as P, D, P inverse, where D is a diagonal matrix with the eigenvalues. We can do it that way, which is perfectly fine. You can do it that way if you wish. However, since this is a Hermitian matrix, we also have the option of writing it in terms of its decomposition with the eigenprojectors. So instead of writing it like this, we could also write it as lambda 1, psi 1 with psi 1. So the projector to the first eigenstate plus lambda 2, psi 2 with psi 2 plus lambda 3, psi 3 with psi 3. Okay. So either way, writing it in the first diagonal form or writing it in the second form with the projectors, both ways will help us in determining the time evolution operator. So remember U, the unitary time evolution operator, is e to the minus r h bar, e to the minus r t over h bar times our matrix H. Okay, so this is a function of a matrix. So we can either use this first option where it's diagonalized with D and then substitute that in. So then this becomes P e to the minus RT over H bar. Sorry, E is in the exponent times P inverse. But then this is just going to be P times, and then the exponential of a diagonal matrix. Remember what we do with that. Whatever the function is, it acts on the diagonal eigenvalues. So the first eigenvalue was -1. If we go back here, minus h bar. So -1 times h bar. So then this will just become, if we go down here, so it will become e to the RT, e to the minus RT, and e to the 3 RT, and zeros everywhere else. Okay, times P inverse. Okay, so you can write it like that. That's perfectly fine. Or if you want to write it with the projector decomposition, we can write U as e to the minus RT over h bar times h. And now using this projector method, it's going to be e to the RT for the first eigenvalue times the projector plus e to the minus RT, substituting the second eigenvalue times its projector, plus e to the minus R3t. Sorry, there's a minus for the e to the minus 3RT times its projector. Okay, so these are equivalents. So the first way is using the diagonalization of the matrix with PD, P inverse. The second way is using the projector decomposition. Okay, both are perfectly fine. You can do whichever one you're more comfortable with. Okay, but they're equivalent. If you multiply out the second option here and multiply out the first option there, you'll get exactly the same thing. Okay, so now that we have our unitary time evolution operators, we can then time evolve a given state. Okay, so let's say we have the state phi. So given state phi, let's say, is 1 over root 2, 1, 1, 0. Find u, the time evolved state, let's call that phi prime. Okay, so we can do it using the first method with the matrix multiplication. So we're going to have P times the diagonal matrix times P inverse, and then times the state vector. So psi prime will be P times e to the RT, 0, 0, 0, e to the minus RT, 0, 0, 0, e to the minus R3t times P inverse, and then times the state. Because remember, operators acting on the state is the same as matrix multiplication with the state column vector. 1, 1, 0. Okay, so this matrix multiplication here, that will give us the new state, phi prime. Okay, so that's the first one using matrix multiplication. If you wanted to do it this other way with the projectors, you can do the same thing. And to make it a bit easier, we can take the state phi and write it as a linear combination of psi1, psi2, and psi3, because we know that psi1, 2, and 3 form an orthonormal basis. So given that psi1, psi2, and psi3 form an orthonormal basis, we can write phi as alpha 1 psi 1 plus alpha 2 psi 2 plus alpha 3 psi 3. Okay, and I'll leave it as an exercise to find alpha 1, 2, and 3. Exercise. Find alpha 1, alpha 2, alpha 3. Okay, and I'll give you the solutions. So alpha 1 is going to be 1/2. Alpha 2 is 1 over 2 root 2. And alpha 3 is 1/2. Okay, so same as alpha 1. Okay, so with this in mind, we can write phi as 1/2 psi 1 plus 1 over 2 root 2 psi 2 plus 1/2 psi 3. Okay, and then using this, we can find psi prime, the time evolved state, by simply multiplying this projector, this linear combination of projectors onto the state. So we have that psi prime is u acting on phi prime is u acting on phi. So that's going to be equal to that projector we had, the sum of the projectors, e to the RT psi 1 psi 1 plus e to the minus RT psi 2 psi 2 plus e to the minus R3t psi 3 psi 3. Okay, so we've got that, and then acting on the state, but we can write the state as this linear combination. So it's 1/2 psi 1 plus 1 over 2 root 2 psi 2 plus 1/2 psi 3. Okay. And then we can just multiply this through. So as a couple examples with some of the terms, multiplying this term onto this term, I'll do that. Let's call that 1. And then multiplying this term on this term, let's call that 2. And then you do the same thing for all the other terms. So for 1, this will end up being e to the RT psi 1 with psi 1 times 1/2 psi 1. But we can write this as 1/2 e to the RT psi1, psi1, psi1. But remember that these states are orthonormal, so the inner product of psi1 with psi1, that's just going to be 1. Okay, so we end up with 1/2 e to the RT acting on psi1. And then for the second term, we end up with e to the minus RT, psi2 with psi2, okay, on 1/2 psi1. This is going to be 1/2 e to the minus RT, psi2, psi2 inner product with psi1. But again, these are orthonormal, so psi2 with psi1, that's going to be 0. Okay, so you can look at all the combinations with the first bracket and the second bracket, and remember that the inner product of the state with itself is going to be 1, and the inner product of a state with another state, a different state, will be 0. So that drastically reduces the number of terms that you have to check. In other words, you're only going to look at the terms of psi1 with psi1, psi2 with psi2, and psi3 with psi3. All the other terms will end up being 0. Yeah, but I'll leave the rest as an exercise. Then if you want to convert this back into a column vector, just look at the definitions for psi1, 2, and 3. So we had them above here. There we go. So psi1, psi2, and psi3, we can write them as column vectors. So our final answer, we can also write as a column vector. But writing it in terms of a linear combination of ket vectors, that's perfectly acceptable. Okay, so you don't need to write it out as a column vector. Writing it out as a linear combination of kets, that's perfectly fine. Okay, you'll get 4 marks for that. Yeah. But if you want to write it out as a column vector, in the case of the first method, okay, where you did matrix multiplication, you're going to end up with a column vector. Again, that's perfectly fine as well. So that's entirely up to you whether you prefer doing it with matrix multiplication, so diagonalize the matrix and then act on the column vector, or if you want to do it the second way, where you write it as a sum of projectors, then you write the state as a linear combination of eigenstates and then do the operation. Both are perfectly fine. Okay, so you'll get the same marks for either method. Okay, so that is it for this revision. Remember that this revision just went over the time evolution. I could also ask you on the probability of being in a certain state. Okay, so remember, if you have a state psi, let's write this out. Psi is equal to C1 psi1 plus C2 psi2, and so on. If I want to know the probability of being in a certain state, let's say psi k, that's given by Born's rule. Okay. So I think there's an H there, Born's rule, where we have psi k with psi inner product squared. That is the probability. Okay, so we also went through this in one of the lectures. So if you want to know the probability of being in a certain state, you have the inner product of the state that you're in with the state that you're checking. You find that complex number, you take the magnitude squared, and that gives you the probability of being in that state. And of course, this is the same as measuring this eigenvalue associated with psi k. So being in the eigenstate psi k, if it's an eigenstate, is the same as measuring that eigenvalue. Same as measuring that corresponding eigenvalue. Okay, but all of that is explained in the notes in the axioms section. Okay, so if you're still having issues with Bourne's rule and measurements and so on, please look through those notes again. Okay, but if you have any questions, please just email me. I will be happy to help you out. Okay, and just a final note, on Monday, the first few tutorials are due. Okay, so I did add that extra time for those that need to catch up. So that's for Monday. For Wednesday, we're having class test 1. And then the following Monday on the 20th, that is when the assignment and tutorial 4 is due. Okay, but all of that is also noted on the course webpage. Yeah, but if you have any questions about due dates or what's coming up, also email me with that. Okay, I'll see you next time.